Hello and welcome to Calculus Lesson 7.4, Vectors in 3-Space. You'll notice that in the top right here, I've got the symbol r to the power 3. I read this as R3. R3 means three-dimensional space. If I had two-dimensional space, I would say R2. And so this is not something that's in the book, although it is something that if you can continue studying this subject matter, you'll see this symbol more and more. Okay, so let's start off with this. Recall. So recall that the point 1, 2 is in 2 space. Okay, so 2 space is R2. Okay, so what does that look like? Let me do a quick sketch. So if I have my y-axis and my x-axis, let's say I plot everything from positive 2 to minus 2 on each quadrant. Okay, so if I do that, then the point 1, 2, it is right here. Okay, and I also know that I can label these 4 separate sections of the Cartesian coordinate system as quadrants. So for example, I have quadrant 1, I have quadrant 2, I have quadrant 3, and I have quadrant 4. Something important to pay attention to here, quadrant 1 is where you have positive x, positive y. Quadrant 2, negative x, positive y. Quadrant 3, both are negative. And quadrant 4, positive x, negative y. Okay, now if you're thinking, wow, that's very simple, then you're right. And we're going to have to understand that and remember those distinctions once we move into R3. Now what I want you to do is, seeing this, I'm going to redraw it. Imagine you take this Cartesian coordinate system and you put it flat. Okay, now you might be wondering, well, it looks flat right now. Assume this right here is vertical, okay, from bottom to top. So bottom to top. Imagine you put it flat on the surface of a table. It would look something like this. Okay, so then there's y1 and 2, negative 1, negative 2 for y. X is equal to 1 and 2 would be here, and negative 1, negative 2 for x would be like so. Okay, and in this case, the point 1, 2, well, here's x is equal to 1 and y is equal to 2, it would be right there. Okay, so the idea is that if I was to connect it, there it is connected to the y, and there it is connected to the x. So I trace out a rectangle. Now, that is what we've been doing so far, and this is something a little new. Imagine putting it flat down. What we're going to do now is introduce the third dimension, hence R3. The third dimension is Z. Okay, and the Z is going to be up and down. So if X and Y are flat on a table, then positive Z is coming up out of the table, and negative Z is going down into the table. Okay, so that's what we're looking at now. So I have X, Y, and Z. All right, so now let's look at the point 1, 2, 2. Now that we're in R3, or three-dimensional space, it doesn't make sense for us to have a two-coordinate point. It makes sense for us to have a point with 3 spaces, one contribution for X, one for Y, and one for Z. It wouldn't make sense to say plot 1, 2 in R3, or to say to plot 1, 2, 2 in R2. All right, so this has values of maximum 2. I'm going to place my axes here, my units on the axes, from minus 2 to 2. So there's minus 2, minus 1, positive 1, positive 2, negative 1, negative 2, positive 1, positive 2, and Z, I'm also going to fill it in. Now, if you're thinking, wow, that looks a bit crowded, you're not wrong. That's pretty crowded. Usually when we sketch three-dimensional renderings, well, first of all, we don't do it that often. We're going to be doing it a lot today because this is 7.4 vectors in 3 space. So that's the whole goal of this section. Usually when we draw three-dimensional vectors in our three-dimensional coordinate system, we usually just draw something like this. We have X, Y, and Z. Generally speaking, X is coming out of the page, Y is going to the right. z is going up. Although sometimes these two x and y do get switched. Okay, so again, we're trying to plot the point 1, 2, 2. What that means is I have to travel 1 along the x direction. So I'm going to show you this with arrows. I'm going to travel a distance of 1 along the x direction. I have to travel a distance of 2 along the y direction. So I'm not going to draw the arrow until here. I have to draw it a little bit behind. I'll show you why. I'm traveling 2 units to the right. Okay, so what that means is what I have here, you see these two lines, this arrow for x and this dotted line, they're parallel to each other. Okay, so you have to remember that the grid here, okay, for x and y, it looks something like this. It's not that the grid lines meet at 90-degree angles from our perspective. While they do meet at 90-degree angles, it doesn't look like that based on the picture. Okay, so our grid lines look something like that. Right? You can see it's on an angle, so that's what we have here. We have this kind of an angle. All right, now we have to go up 2 units, so we're going to go up 2, something like that. Okay, all right, so we have 1, 2, 2. That means the vector 1, 2, 2 is going to go from the origin to this new point. So actually, let me label that point here. So that's the point 1, 2, 2. So the vector 1, 2, 2, or rather the position vector that goes from the origin to that point will look something like that. Okay, so this is the vector 1, 2, 2. It's a little hard to see there, but it's that dark blue line. Okay, so wherever you start to wherever you finish. Now something interesting to point out here. You see how I discussed the 4 quadrants here? The prefix for that is quad, meaning 4. I don't have 4 regions anymore, I have 8. And so I don't have quadrants, I have octants. Okay? There are 8 octants. And we're going to describe what each of these are. Okay, I'm going to describe this by showing you a simulation. All right, so let me just swap screens here for a moment. Okay, hopefully you can see what I've got here. It's a nice applet. I'll post the links and you can also play around with it. You can adjust the x value with this slider, the y value with this slider, and the z value with this slider. But what I really want you to notice is that I have 8 quadrants. There are 8 regions here in total. Okay, so what I want to do, now give me a moment while I try to configure this. I want to have y pointing up and x pointing to the right. So hang on. It's a little tough to get this 3-dimensionally rotated because after all we're, oh, there we go. Okay, so take a look at that right now. This is what you're used to. I've got positive y up, positive x to the right. I've got a point here. It's 1, 2, 2, and that's exactly the point that I was just working with. So you can see from this perspective, this is just the xy plane. The only way I can understand z is that z is coming out of the plane, positive z, at me, and negative z is going into the page. Okay, so I can see here the x is equal to 1 unit, I can see the y is equal to 2, but I can't make out the fact that z is equal to 2. So in order to understand that, I have to change my perspective, right? So here we go, I'm gonna move it like so. Okay, so now it's a little bit easier to see. I still have x is equal to 1, y is equal to 2, and now I have z is equal to 2. And sure enough, you see this red line here. This red line is the resultant vector. So let me just put it like that. It might be easier to see. There we go. X is coming out of the page, y is going to the right, z is going up, and you have the x, y, and z components. There's that point. And so the vector is the same as the point here, just with square brackets on the ends instead of round brackets. Okay, so given that, we're going to try to figure out, given the following 4 sets of points, we're going to try to figure out which octant it's in, and then we have to describe that octant. So before we get to that example, let me just explain to you how we are going to describe the octants. Okay, so if we look at it from this point of view, okay, so x is coming out of the page, y is going to the right, z is going up. This right here, okay, so this top section right here, this is the first octant. And if you look at that green square right here, this would have been the first quadrant. You have positive x and positive y. And so now instead of having that square, I have this almost cube-like shape here. This octant here, that 1/8 of the region, that's octant number 1. And it kind of corresponds to quadrant 1, except just remember this. Wherever you have quadrant 1, that's where you have octant 1. Just make sure the z values are positive. All right, now where would you have quadrant 2? Well, quadrant 2 would exist where you have positive y values and negative x, right? So that's the green square. And so as long as our z values are positive, so this region right here, okay, this is going to be octant 2. Rotate again. Where would quadrant 3 be? Well, quadrant 3 would have negative x and negative y values, and that's this green square. And so this 1/8 of a region here, that's octant 3. And sure enough, if we rotate, here we have positive x values and negative y values. This is quadrant 4, and so when you have positive z values as well, that's octant 4. Okay, so let's complete the 360-degree rotation. We have figured out the names of the regions on top. Okay, so we are back again here now at octant 1. Right below octant 1, okay, so you still have positive x, positive y, but now we're in the negative z. That is going to be octant 5. Okay, so octant 5 is directly below octant 1. And again, if you turn, okay, so again, this green square here, this is quadrant 2. Okay, below quadrant 2, you have octant 6. Okay, and then down here, octant 7. And finally, octant 8. All right, and then now we're back to where we started. There's octant 5, and then coming back up here, there's octant 1. So I hope that's okay. Now, I know that was a lot of me talking and you watching, but this is unfortunately what we have to get through. I'm going to go back to the page here for a moment so then I can write down the description of these octants. Okay. So when we have, for example, octant 1 is also known as top. Oh, hang on a second. This marker is dead. Let me try this one. Octant 1 is top, front, right. Okay, top, front, right. I just want to make sure that you understand how this works. Let me go back to the simulation for a second. Okay, so remember we have x coming out of the board, y is going to the right, z is going up. So if we say top, so that's positive z, front, that means we're in these two sides now, and right, that means we're right here, right? Or rather, in this big cubic space here. So top, front, right, that's quadrant 1. I'm going to go ahead and write the rest of them, but feel free, go to the link in the animation as you're going through the video, and make sure the rest of these descriptions make sense to you. Okay, so quadrant 2, we can also describe it as top, back, right. Quadrant 3, top, back, left. Okay, quadrant 4, top, front, left. Quadrant 5, bottom, front, right. Quadrant 6. Okay, so if anything, you're learning your Roman numerals now. 6 is bottom, back, right. Seven. This is bottom, back, left. And finally, quadrant 8. This is bottom, front, left. Okay, so we have all of the quadrants, or sorry, octants there. And so we're going to now look at a set of 4 various points in 3 space, and we are going to not only determine which octant they're in, but also describe the octant that they're in. Okay, So let's look at the first point here. So we are moving into example 1. Okay, so describe the octants. Okay. So part A, we have the point 1, 2, 3. All right, 1, 2, 3. Well, all of those coordinates are positive, right? So I mean, you should already surmise that we're going to be in octant 1. Okay, so this is octant 1. Octant 1 is top, front, right. Okay, so if we wanted to look at 1, 2, 3 in the simulation, let me actually just get that open here. So going to that screen, 1, 2, 3. So if I adjust x right now, x is already 1, y is already 2. So to adjust z to 3, I just move this up 2 times. So there it is. Okay, so that is showing you where it is. That is definitely in octant number 1. Okay, we won't do this for every single one, but just to give you an idea. So for B, we have -3, 2, 1. X is negative, but y and z are both positive. If you want, feel free to pause the video and try to figure out where this is for yourself, and then come back to this. Well, this is going to be in quadrant 2. Okay, this is top, back, right. And we'll do 2 more. C, -3, -2, -1. All of them are negative. Where is that going to be? So that is going to be an octant 7. Okay, so this is bottom, back, left. And finally, D, point 1, 2, -3. This is going to be in quadrant 5. And we describe this as bottom, front, right. So a lot of descriptive names here. Okay, I hope that is okay. Just moving around some markers here. Give me a moment. Okay. So the next thing I want to do is plot some points in R3, in 3-dimensional space. So I'm actually going to move and use a separate piece of paper here because this is going to be a big picture. So let me move up here. All right. So example 2. I'm going to sketch one of these by hand to show you how to do it, and the other one I will show you using the computer simulation. Okay, so example 2, plot points in R3, 3-dimensional space. So part A, plot the points A, 2, 6, 1, and B, -1, -3, -4. Okay, so like I said, I'm going to plot one of these by hand, and the other one I'm going to use the computer simulation. So I'm going to plot B by hand. Okay, so I'm going to go ahead and sketch my Cartesian coordinate system here, but my 3-dimensional Cartesian coordinate system. So go ahead and grab your ruler, and I'll do the same. So I'm going to sketch my octants here. Okay, so there's X. Y is going to cut that in the middle. And Z is going to be up and down. So X, Y, Z. Now notice that, well, at least for B, the biggest number I reach is 4, but for A it's 6. Let's just go up to 6. So or -6 to 6. So -6, that's going to be -4. That'll be -2. 2, 4, 6. Okay, and of course there's the halfway points as well. Okay, x-axis is done. For the y, I'm also going to go up to 6. So there's 6, 4, and 2. And -6, -4, -2. And then complete your z as well. There's 6, 4, 2, -6, -4, -2, and all the halfway points. Okay, so we're going to plot B here. So for B, B is -1, -3, +4. So what I want you to remember is that the -1, that's x, -3, that's y, and -4, that's z. Okay. So, oh, I'm sorry, that should be +4. +4. Okay, so that's +4 in the z. All right, so -1 in the x, that means starting from the origin, I move -1 in the x direction. Okay, and then I move -3 in the y direction. So notice for the x, negative x means I'm moving in the negative x direction by 1 unit. -3 for the y means I'm moving in the negative y direction. Positive y would be to the right, so negative y is going to be to the left. So I'm moving 3 spaces to the left. So it's going to look something like this. Remember, I'm not drawing it all the way to -3 because I'm starting from here. So my grid lines, if you can imagine, they're going like this. Okay, so that means what I would have here is I have almost like a rectangle drawn there on the XY plane. Now I have to go 4 units up. Okay, so 4 units up, it's going to look something like this. So what I want you to see here is that what I've actually traced out is, well, a rectangular prism. The base of that rectangular prism is here. The height of that rectangular prism is 4. So that means from here, it's also going to be a height of 4. Okay. I'm going to connect these points. Now, I also have a height of 4 from this side. I'm going to connect it here, connect this, connecting that, and it's coming all the way down. So really what you have, like I said, you have a rectangular prism traced out by these 3 vectors. So moving -1 in the x, -3 in the y, and +4 in the z. Okay, so notice that this line lines up with the +4 on the z-axis. So we trace out this a rectangular prism, like I keep saying. Now B, notice that it's in the top, it's in the back, and it's on the left. Okay, so if I look at my descriptions, top, back, left, where does that show up? Right here. So that's octant number 3. Okay, now for the other one, for A, I'm going to go ahead to the applet here, and I'm going to show you what it looks like. So let's switch over to the screen. All right, so here we want the point 2, 6, 1, and there it is, 2, 6, 1. So like I said, you can actually play around with these scrolls and figure out where it's going to be, but this is essentially where you have it. Notice that in this quadrant, I have positive x values. I've got positive y values. Let's see here. So that means we're going to be in octant number 1. And sure enough, that's going to be front, right, top, right? So we have to organize it like this. So it's in the front. This would be the front. It's on the right, and it's on top. Okay, so let's go back to our page here. Okay. So A, we saw was front, right, top, and it's in quadrant number 1. Now I want to show you something else here. Okay, so I drew each vector individually. Okay, so that is the point that I'm interested in for point B. So let me just, that's point B, right? But if I want to show and represent the position vector going from the origin to point B, I take my marker and from the origin I draw a vector going to point B. So it looks something like that. Okay, so that would be the vector OB. All right, so this is a position vector since it's starting from the origin. Now, whatever point you have, any point that you have in space, it's going to have some x-coordinate, it's going to have some y-coordinate, and it's going to have some z-coordinate. Let's say the coordinates are x1, y1, and z1. So this is your point. Now, my vector, so let's say we call V OB, or it can be OP, whatever the point happens to be. My vector V, which is OB in this case, or it can even be OP, again, doesn't matter. this is going to be the vector x1, comma, y1, comma, z1. And like I said, this is a position vector because it starts from the origin and it goes to the point whose coordinates are the same as that for the vector. So we're going to be using this idea more and more throughout this lesson. Okay, let's move on. What we're really trying to show here is, well, not just how to treat three-dimensional space, but we're also going to look at very much so how much there is a similarity and symmetry between R2 and R3. Okay, so first, let's go back to the idea of unit vectors. Specifically, we're looking at the basics unit vectors here. So in two-dimensional space, so recall, in R2, okay, so here's my y-axis, here is my x-axis. Recall that in R2, I can have a vector of length 1 along the x-axis, and I can have a vector of length 1 along the y-axis. So let me just note that here on the scales. If a vector has length 1 and it's along the x-axis, we call that I. Now in the previous video, you would have seen me use the symbol hat, and usually we call this I hat, but like I keep saying in this book, they don't use that symbol. So just know in the future that they are the same. And the unit vector, the vector with length 1 in the y direction, it's called j. Okay, so I, in two-dimensional space, is the vector 1, 0. It has magnitude 1 in the x direction and magnitude 0 in the y direction, right? It doesn't have any component along the y. Now for j, it has 0 pieces along the x and it has a length of 1 in the y direction. All right, so how does this connect to R3? Well, let's take a look. Now, in R3, well, we have something that looks like this. Here's x, here's y, and now we have this extra dimension, z. Okay, so now we have still, same idea. Vector I is a vector that has length 1 in the direction of x. And we can also have vectors of length 1 in the directions of y and also z now. Now, the vector of length 1 in direction of x is still called I, but what you have to remember now is that I is in three-dimensional space. So its position is given by a set of 3 coordinates, not 2 like here. It has to be given by 3. So in the x dimension, it has a length of 1. In the y dimension, it has a length of 0. And in the z dimension, it has a length of 0. Okay, for j, j has a length of 0 along the x, 1 along the y, and 0 along the z. And finally, z has a length of 0 along the x, 0 along the y, and 1 along the z. So we now have the 3 basis vectors, the 3 basic unit vectors in three-dimensional space. Okay. Now, given those vectors, so what I want you to be comfortable with is representing any kind of vector with the unit vectors in three-dimensional space. So for example, if I have vector u, and that's given by a, comma b, comma c, I can rewrite that a couple of different ways. I know that it has a magnitude of a in the x direction, it has a magnitude of b in the y, and magnitude c in the z. In fact, I can take this vector and split it up into 3 separate vectors, the sum of 3 separate vectors. And if you recall, 2 lessons ago, we actually did exactly this. Okay, so for example, I can break this up into a0, 0 plus 0, b0 plus 0, 0, c. If I add all 3 of these vectors, I will end up with exactly what I have here. Remember, when you add vectors, you just add the respective components. So the x component would be a plus 0, which is a. The y component would be 0 plus b plus 0, which is b. And the c component would be 0 plus 0 plus c, which is c. Now, this I can rewrite as, if I factor out the a 1, comma 0, comma 0, plus b 0, comma 1, comma 0, plus c 0, comma 0, comma 1. And sure enough, these 3 things are I, j, and k respectively. So I have a times I plus b times j plus c times k. And so pretty much what I get to is that I can rewrite the vector u like this or like this, any of those ways. They're all the same thing. So be comfortable seeing the vectors in any of those forms. Now, that is rewriting the vector. How do we find the magnitude? So if you remember, when we had two-dimensional vectors, the magnitude was really simple. We just used Pythagorean theorem, right? So if you had, let's say, here's your x, here's your y, you had some kind of a vector like this, it had some x piece, let's say the x length was 2 and the y height was 3, then the hypotenuse would be, well, the square root of 2 squared plus 3 squared. Right, so what is that? 9 plus 4 is 13, so square root of 13 was the length of that vector, the magnitude. In 3 dimensions, it's very much the same. It's just an extension of Pythagorean theorem. And so the magnitude of u is going to be the square root of the sum of the squares of the individual parts. A squared plus b squared plus c squared. So if you're not sure, or that's not sitting well with you for some reason, just go back to the app for a second. Well, actually, we'll go back. If you look, I actually really like this applet because it shows you each of the pieces here. Now, what I want you to notice is that you see this line here. This is the distance along the y. That's, well, let's take a look here. That's 6 units, right? So from here to here, that's 6 units. The x, that's 2 units. Right? So just look at x and y. If you wanted to find the magnitude of just x and y, so if you were just in quadrant 1, the length of the sum vector for x and y is this diagonal line right here. Let me just zoom in on this a bit. I wonder if I can zoom in. There we go. The magnitude of y and x is this diagonal line, right? So this diagonal line is essentially the square root of x squared plus y squared. Now take that line and add this line. So if you add these two vectors together, you get this red line, the resultant. And sure enough, if this is the square root of x squared plus y squared, if we square that side, you'll just have x squared plus y squared. And if you add z squared to that, you'll have x squared plus y squared plus z squared. And then the square root of that sum is the length of the red side right here. I hope that makes sense. If not, just take a bit of time to really study it. And if you're still having trouble, let me know and I'll see if I can find a different way to explain it to you. But for now, that is the formula. Okay, let's try to do some examples. Okay, so example. Now I have actually lost track of what we're at, so this will be an informal example, not a formal one. So for vector u, which is 3 minus 1, 2, well, let's figure out the magnitude and let's figure out the direction. Well, the direction for u, a couple ways. You can either state that it's in the direction 3, negative 1, 2, and I guess actually the discussion of the direction of u is not really that much significant here. It's not very important. But we will find the magnitude here. Okay, so what I'm going to have you do is you're going to come back to this applet here. So let's go back here. And we're going to open the vector 3 minus 1, 2. So right now I have 2, 6, 1. Let me zoom out a bit. So I need 3 for x, so I'm going to adjust this. 3, I need minus 1 for y. And I need 2 for z. There we go. So here I am. Okay, positive x, negative y, positive z. Okay, so there I am. The magnitude of that vector, so let's go back to the page here. So if u is that size, the magnitude is the square root of 3 squared plus negative 1 squared plus 2 squared, and that's, well, what is that? 9 plus 1, that's 10, plus 4, that's 14, so root 14 is the magnitude. And just another thing I want to show you is that this vector we can also rewrite as 3i minus j plus 2k. Same thing. Okay, so really what we're trying to get at here is that properties of vectors, they're very much the same in 2 dimensions and 3 dimensions. Okay. So let me just write that down so you also have it in your notes. Properties in 3 dimensions are same as in 2 dimensions. Okay, so one example of this would be scalar multiplication. And we're going to go through many of these examples in the lesson today. Scalar multiplication. Let's say you have vector u, and this is in 3 space, of course. So vector u is given by the vector with components u1, u2, u3. Okay. And k is an element of the real numbers. It's a constant. And so therefore, if I have k times u, the new vector is going to be ku1, ku2, ku3. So you take that constant and you multiply to each individual dimension of the vector. Okay. Now, what I can see here is that ku is collinear with u. So ku is collinear with u. Okay, so that was a piece of vocabulary that we learned earlier on. Collinear means the vectors are parallel. And so if you place them tip to tail, they would form a straight line. All right, so now with that in mind, let's try a formal example. So I think we're on example 3 now. So find a, so that's letter A, such that square bracket 1, 2, 3, and square bracket 2a6 are collinear. Okay, so that's going to be part A of the problem. All right, so find A such that these two are collinear. Remember, if they're collinear, that means they're also parallel, and that also means they're scalar multiples of each other. Right, so we just saw that here. Scalar multiples means they're collinear. So therefore, collinear means they're scalar multiples. So what that means is I have to find the k value such that when you multiply k to one vector, you get the other vector. I mean, that's the whole idea. So if I multiply k by 1, 2, 3, let's say, I need to get 2, a, 6. And whatever constant that is, it has to be the same constant for every single term, hence why it's outside. So what do I do to get from 1 to 2? Well, to get from 1 to 2, I have to multiply by 2. How do I get from 3 to 6? Well, it's the same, and that's what you would expect. I have to multiply by 2 to get from 3 to 6. So if I multiply 1 and 3 by 2 to get to 2 and 6 respectively, that means I have to multiply 2 also by 2 to get a. So that means k is equal to 2, so therefore this 2 times 2 is going to equal a. So 2 times 2 is a, so therefore a is equal to 4. Has to be the same scalar multiple. Okay, let's try part B. Find B and C such that bracket negative 2b7 and bracket C621 are collinear. So this can be said anyways. Show that they are parallel, show that they are scalar multiples, show that they are collinear. So I'm trying to show that these two things are scalar multiples of each other. So that means some constant times one vector, so negative 2b7 has to equal the other vector. Now it doesn't matter which side you put k. They're scalar multiples of each other. So you can put k on the left or you could put k on the right. The only difference is if you put k on the left, you're going to get one value of k, like I did here. I got k is equal to 2. If I stick k on the other side, you're going to get a different value for k. Right? So for example, if you went backwards here, how do you get from 2 to 1? You have to multiply by 1/2, right? How do I get from 6 to 3? I have to multiply by 1/2. And how do I get from a to 2? I have to multiply by 1/2. So what number times 1/2 is equal to 2? 4. Right? So it just means you're going to get a different value. But they have to be scalar multiples of each other. It doesn't matter which side you put k, because k can be any number. It can be between 0 and 1, or it can have an absolute value greater than 1. Okay, so let's see if we can figure out what this scalar multiple is. So I'm going to set up a series of equations here, since I have 2 variables here, 2 unknowns, as opposed to 1 like I had before. Rather, I actually have 3. I have b, c, and k. So to solve a series of 3 unknowns, I need 3 equations according to mathematics. So I'm going to set up 3 equations. So -2 times k is equal to c. That's going to be my first equation. The second equation is going to be b times k is equal to 6. And my third equation is going to be 7 times k equals to 21. So really you just have a series, like I said, 3 equations, 3 unknowns. You have to isolate for them, for one variable, plug it in the other equation to find your unknowns. The nice thing is, in this particular example, I can right away figure out the value of k from equation number 3. 7 times k is equal to 21. So what has to be k? Well, k has to be 3. If k is 3, I'm going to plug that back into equation 2. Okay, equation 2 is b times k is equal to 6. So that means 3 times b is equal to 6. So what is b? b must be 2. And now to find c, so we're going to now plug this into equation 1. -2 times k, or -2 times 3, is equal to c. So therefore c is equal to -6. So there you go. So b is 2, c is -6. Okay. So far we've seen that scalar multiplication is the same in R2 and R3. So moving on. The next thing that's also the same is vector addition. Okay, so if I have, let's say I have 2 vectors, u, so u is going to be u1, comma u2, comma u3. And I have vector v, which is v1, comma v2, comma v3. If I add those vectors together, u plus v, well, that means I add my x values, so that's u1 plus v1. Let me just move those commas a little bit to the left. Okay, vy is going to be u2 plus v2, and the z is going to be u3 plus v3. So that didn't change. Vector subtraction is very much the same. Okay, you're dealing with the same 2 vectors, u and v. So if I have u minus v, it's going to be u1 minus v1, comma u2 minus v2, comma u3 minus v3. So this is how I take the difference of those 2 vectors. Okay, so a few lessons back, we looked at how to determine the vector that exists between 2 points in space. And just like we did in 2 dimensions, it's the same in 3 dimensions. So let's just move that like this. Okay, so if we want to look at a vector between 2 points, okay, so let's say we have point P1, and that's given by the coordinates x1, y1, z1, and point P2 is given by the coordinates x2, y2, z2. Well, the vector going from point P1 to P2 is going to be x2 minus x1, comma, y2 minus y1, comma, z2 minus z1, and that's it. Now, it was based on this conclusion that we were able to determine the magnitude of the vector between 2 points in R2. So the same is going to apply in R3. We're just going to extend it. So magnitude of vector between 2 points. Okay, so the magnitude of this vector, so the magnitude of P1, P2, well, we just take the sum of the squares of each dimension, and we square root the total. So the square root of the sum of the squares of each dimension. So x is x2 minus x1, y is y2 minus y1, and z is z2 minus z1. So that should look like the distance formula, except now we're applying it to 3 dimensions. Okay, let's move on to an example. So now we are at example 4. Okay, so part A. Given point A, which is 3, 6, -1, and point B, just turn that, and point B, which is -1, 0, 5, express vector AB as an ordered triple. Okay, then write in terms of I, J, and K. Okay, so let's do part A first. So we have to write down the ordered triple. The ordered triple just means write down the vector as a vector with square brackets. Okay, so this means something like this. X, y, z. Whatever the values are, they go in those particular slots, and you put the square brackets around. Okay, so we have these 2 points in space. We have to figure out the point AB. So that's essentially doing this step right here, finding the vector between 2 points. So if you have 2 points, P1 and P2, or here, A and B, the vector between the 2 points, you subtract the x, the y, and the z values from each other. So that's what we're going to do. So AB is equal to, so we're going to subtract these 2 vectors from each other. So it's going to be B minus A, so -1, 0, 5, minus 3, 6, -1. So you know, this means that you have to deal with x, y, and z all separately. So -1 minus 3 for x, 0 minus 6 for y, and for z, 5 minus -1. Okay, so that is equal to -4, -6, 6. So this is the ordered triple, and we can also rewrite that in terms of I, j, and k as -4i minus 6j plus 6k. So these 2 things are the same. Okay, so that's A. Part B asks us to determine the magnitude of vector AB. Well, you know how to determine the magnitude of the vector. It's right here. The magnitude of the vector between P1 and P2, add the sum of the squares of each component, and then square root the whole thing. Well, I already have the pieces here. So the magnitude of AB is going to be equal to the square root of -4 squared plus 6 squared. Sorry, that's -6 squared plus 6 squared. Okay. So what does that equal? Well, if we actually grab our calculators, let's see. So we've got, well, -4 squared and 4 squared are the same, so I'm just going to plug in the absolute value. So that's 4 squared plus 6 squared plus 6 squared, 88. So we'll call that square root of 88. Now, if you're looking at that and wondering, well, can I express that in simpler form? You're absolutely right. So let's do that. 88 we can break down into a lot of ways. Like, for example, that can be 11 times 8. But 11 and 8 we can break down further. So why don't we just break that down right away into something times 4. 88 is equal to 22 times 4. So this is root 22 times root 4. And square root of 4 is 2. So that's 2 root 22. And then 22 is 11 times 2. Well, that doesn't really help us anymore. So that's as far down as we can get it. This will come in handy for the next part. Okay, part C. Determine a unit vector u in the direction of AB. Now, you see, we found the magnitude of AB to be 2 root 22. Okay, so what is that? Let's take a look. 2 root 22. That's about 9.4, let's say. If the magnitude happened to be 1, then my answer would just be whatever the vector AB turned out to be, which is right here. But this vector doesn't have magnitude 1. It has magnitude 9.4 approximately, or 2 root 22. So remember, in order to get the vector to have magnitude 1 but keep it in the same direction, you got to take that vector and divide it by its magnitude. So u is going to be a unit vector in the direction AB. So I take the vector AB and I divide by how big it is. Excuse me. So that's by its magnitude. So AB is the vector -4, -6, comma 6, and I'm dividing that by 2 root 22. Now I don't want to leave it like that. I want to write it a bit nicer. So what I'm going to do is rewrite it like this. So 1 over 2 root 22 times -4, comma -6, comma 6. So this way it's a little bit clearer to me that I have to take this constant and distribute it to each part. Because what you actually have here is you have a constant times u, right? So you can take that constant and multiply it inside to each component of that vector. So then that's going to be equal to -4 over 2 root 22, comma, -6 over 2 root 22, comma, +6 over 2 root 22. And as a final step, I'm just going to simplify this. -4 divided by 2, that's -2. So that's -2 over root 22. -6 divided by 2 is -3. So that's -3 over root 22. 6 divided by 2 is 3. 3 over root 22. So there we go. There is the answer to part C. Okay, so we've seen that vector addition, we've seen that scalar multiplication, all of that, it's the same from R2 to R3. Now let's look at dot product. Okay. If you haven't noticed yet, this lesson is a bit long. Dot product in R3. Okay. So again, we are dealing with the two vectors u and v, and u and v will be represented as follows. Okay, so there are my vectors u and v. The dot product u dot v, same as before, we're going to take the sums of the products of each dimension. So u1 v1 plus u2 v2 plus u3 v3. Okay, and that's really all it is. So let's make sure that is okay by doing an example. So given u, which is 2, 3, -5, v, which is 8, -4, 3, and w, which is equal to -6, -2, 0. Simplify each vector expression. Okay. So for part A, we're going to find out what -3u is. For part B, we're going to find u plus v plus w. For part C, we're going to find the absolute value of u minus v. And for part D, we're going to find u dot v. So same things that we've been doing in R2, except now we're just expanding and applying it to R3. Okay, let's start with -3u. This is a scalar multiple. We're going to multiply the vector u, every single component of it, by -3. So this is -3 times 2, comma 3, comma -5. So just multiplying that inside, -3 times 2 is -6. -3 times 3 is -9, and -3 times -5, that's +15. So there's -3u. Excuse me. Okay, part B, we're going to have u plus v plus w. So we're just adding three vectors together. So just make sure that you understand that when you add vectors, the result will be a vector. Okay, so here we go. So u 2, 3, negative 5, plus v, 8, negative 4, 3, plus w, negative 6, negative 2, 0. So add the x's together, add the y's together, add the z's together. 2 plus 8 is 10, minus 6 is 4. So let me just actually write that all out. 2 plus 8 minus 6 for x, 3 minus 4 minus 2 for y, and negative 5 plus 3, and then plus 0 for z. Okay, so we said this was 10 minus 6, so that's 4. What is this? 3 minus 4, that's negative 1. Minus 2 is negative 3. And negative 5 plus 3, that's negative 2. So there's our result. Okay. C, the magnitude of u minus v. Okay. So u minus v, that's going to be a vector. Just like we have a vector when we add vectors, when you subtract vectors, you still have a vector. The fact that we're looking for the absolute value means that our final result will be a number. So this is going to be magnitude of u, so u's up here. So 2, 3, negative 5, minus v, 8 minus 4, 3. So when you subtract two vectors, you get a vector. 2 minus 8 is going to be the x. 3 minus negative 4 is going to be the y. And negative 5 minus 3 is going to be the z. Okay, so what do we got here? 2 minus 8 is negative 6. 3 minus negative 4, that's 3 plus 4, which is 7. Negative 5 minus 3, that's negative 8. Okay, so how do we find the magnitude of a vector? Well, we've seen this. It's just an extension of the Pythagorean theorem. So I take the square root of negative 6 squared plus 7 squared plus negative 8 squared. And if I do that, let's see what I get. So negative 6 and 6 squared are the same. So I'm just going to put it as positive 6 squared plus 7 squared plus 8 squared. Oops. It's 149. That's not going to square root nicely, so I'll leave the answer as square root 149. And our answer is a scalar as we expected. Now finally, u dot v. U dot v, dot product, should also return a scalar value. So you're expecting a number as your final answer. So I am dotting these two vectors. Okay, so u is 2, 3, negative 5. V is 8, negative 4, and 3. Okay, so dot product means I multiply the x's, I add that to the product of the y, and I add that to the product of the z's. So 2 times 8 plus 3 times negative 4 plus negative 5 times 3. Just a series of calculations here. Okay, so 2 times 8 is 16. Negative 3 times 4, that's negative 12. And negative 5 times 3, that's minus 15. So if you combine all of these together, that's going to be 4 minus 15, that's negative 11. Okay. So hopefully you're doing okay so far. I know this is a bit long. This is just past the halfway point of the lesson. Okay. So now we're going to do some more examples. Okay. We are now at example 6. Determine if the vectors A and B are collinear. Okay, so here is vector A. A is 6, 2, 4. And B is 9, 3, 6. So now remember, in order to be collinear, well, there's a couple ways of saying this. That means they're scalar multiples. It also means they're parallel, which also means that they're scalar multiples. So it's going to be the fact that they're scalar multiples that helps us here. Although I'm going to show you another method here as well. So we have two methods to solving this problem. Okay, so method one, we can do the same thing we did before. So if they are scalar multiples, that means there's some constant that you can multiply to one vector to get the other vector. So if they are collinear, so it's not like we're told to find some letter value because we know they're collinear. We're told to find if they are collinear. Excuse me. If A is collinear, so if A is parallel to B, then A is equal to some constant times B, where K is an element of the real numbers. And of course that can go the other way around as well. So let's see here. I might actually write it so that the K is on the left, because I noticed that these numbers are smaller overall compared to the ones on the right. Like I said, it doesn't matter which side you put the K. I'm used to writing it on the right, but for this I'm gonna write it on the left. So K times A is equal to B. Same thing. All right. So let's see if there's a constant where when I multiply to 6, 2, 4, I get 9, 3, 6. There might not be, and this is why you have to check every single entry. If it's not the same K value for all three dimensions, that means they're not scalar multiples. Even if it matches for 2 dimensions and not for the third, they're not scalar multiples. So if we look at the X dimension, I can see that 6 times K is equal to 9. If I look at the Y dimension, I can see that 2 times K is equal to 3. And if I look at Z, I can see that 4 times K is equal to 6. So that's really why I stuck K on the left, because it's easier to figure out a K value such that your number gets bigger, for me anyways, compared to if it's getting smaller. Okay, so K, well actually it's probably easiest to find K from Y. K is going to be 3 divided by 2, or 1.5. Okay, so check the first one. If you multiply 6 by 1.5, so by itself and half of it, you're going to get 9. Okay, what about the last one? 4 times 1.5, sure enough, that's 6. So since K is the same for all three dimensions, therefore the vectors are indeed collinear. So since K is equal to 1.5 for all three dimensions, therefore A and B are collinear. Okay, so that's the method that we've used up till now. And like I said, there are two methods here. That is the first. Okay, so the other method to use, and arguably I think this one's actually faster, but who knows? You might think of the other method first, and maybe that method's going to be faster for you. So the other method to use here is the dot product formula. If two vectors are collinear, or they're parallel, one way of looking at it is, yes, they're scalar multiples of each other, but the other way to look at it is if two vectors are parallel, well, what's the angle between them? So if I have A and B, they're parallel, the angle between them is 0 degrees. So if I was to inspect the dot product between A and B, it's going to look like this. A dot B is equal to magnitude of A times magnitude of B times cosine of theta. So what I'm saying is that theta is equal to 0 degrees. So what's cosine of 0? That's 1. So what that means is that A dot B is equal to magnitude of A times magnitude of B. So, I mean, this could be another way to determine the answer. Okay, so if you have A dot B is equal to magnitude of A times magnitude of B, you can most likely rearrange this equation and we'll try to figure out what you have here. By solving for A dot B, so that's going to be a scalar, and then solving for magnitude of A and magnitude of B, well, that's also going to be a scalar. If these two numbers are exactly the same, so if A dot B is equal to mag A times mag B, that means that cosine of theta must have equaled 1, which in turn means that cosine of 0 degrees was, well, 0 degrees was the angle. Okay, so that's the other way to do it. Okay, so if you have cosine of theta, and that's equal to A dot B over mag A times mag B, you have to solve this to show that theta is equal to 0 degrees. This would be the other way to do it. I'm not going to go through the full solution because I think you're able to do that, but I'm not going to spend time to do that right now. Okay, we are officially in the last 20% of the lesson, so let's keep going through. Example 7. Okay, so just before I move on to the example, there's a little bit of a theory here. Recall that A and B are perpendicular. Sorry, A and B, so vector A and vector B are perpendicular. Now, you see this IFF, you might have forgotten what that means. That means if and only if. Okay, so they are perpendicular. Another word for perpendicular is orthogonal. We're going to be using that word more and more. So A and B are perpendicular or orthogonal if and only if their dot product is 0. So we saw that back in R2, and this is still the case. The reason being that when two things are perpendicular, the angle between them is 90 degrees. And in the dot product expression, I have cosine of theta. Cosine of 90 degrees is 0. So that sets the whole thing to 0. Okay. Let's do the example. Find a vector that is orthogonal to 3, 4, 5. Okay. Notice the wording of the question. It says find a vector, not find the vector. That means there's more than one answer here. And if you can really understand this visually and geometrically in your head, there are an infinite number of vectors perpendicular to this. Okay? So this means I have to find a vector x, y, z such that their dot product is 0, such that 3, 4, 5 dotted with x, y, z equals to 0. Okay, well, I know how to expand the dot product. This is going to be 3 times x plus 4 times y plus 5 times z. So I just have to come up with x, y, and z values that set this to 0. And like I said, there's going to be more than one answer here. Okay, so one possibility is positive 4, negative 3, 0. Okay, so why does that work? Because if you have 3 times 4, and actually the other one would have worked too, 3 times 4 plus 4 times negative 3 plus 5 times 0, that's positive 12 minus 12 plus 0 equals to 0. Okay, and that's exactly what you want. What you have to be careful of, don't use 0, 0, 0. Okay, so that is the 0 vector in R3. So the 0 vector is just the vector that has 0 in spaces of the dimensions. If you plug in 0, 0, 0, that's not technically a vector that has any kind of length. So do not use that. You can use 1 or 2 of the components as 0 and then plug the other one in as a value. Well, you wouldn't be able to set 2 of them equal to 0. You would have to set only 1. Otherwise, you wouldn't be able to cancel out the first term. Okay, so don't use the 0 vector there. But there are multiple answers. Even minus 4, plus 3, and 0. That works too. Okay, last example. Okay, example 8. This is similar to the first example we did in the way that it has to do with physics. So imagine a construction site. Okay, so at this construction site, there are metal beams being lifted. Okay, so this is your metal beam. It's very heavy, so it's getting lifted up. Now there is some force acting on it. Okay, so there's some force acting along the cable that's pulling it up, but maybe there is some kind of wind and maybe it's getting pulled from some other direction. Overall, there are going to be 3 forces acting on this. Okay, so I'm going to sketch the 3 forces in using green. We have a force F1 acting up. I have a force F3 acting to the left, and I have a force F2. Well, this one is acting perpendicular to those ones. Now this situation is unique in that there are 3 forces and they're all perpendicular. Let me try to focus the camera here. There we go. Okay. So something to notice. So here, let me write down the forces. So F1 is 5,000 newtons up. Notice up is not the same thing as north. Okay, north, northeast, southwest, that's on the plane parallel to the ground. Okay, north is not up. Up is perpendicular to north. F2, that's going to be 650 newtons north. So this is north. And F3 is 600 newtons west. What we have to do is find the magnitude of the resultant force. Let me just write that down. Find the magnitude of the resultant force. Now, this question is a little bit unique in the sense that all 3 forces are perpendicular to each other. And so when you add things that are perpendicular, so for example, if I added F1 and F2, well, I would get another vector. So here's F1 that's up, F2 is north. The sum, F1 plus F2, it's going to look something like this, right? Now, what you have to visualize is that this sum, F1 plus F2, it's in a plane that's perpendicular to F3. So then if you add F1 and F2, whatever sum that is, with F3, that means you're adding 2 vectors that are perpendicular with each other. So therefore, adding F1 with F2 with F3, this is essentially adding the x, y, z components of a standard vector. So we need to use the extended version of Pythagorean theorem. So the resultant is F1 plus F2 plus F3. And since they're all perpendicular to each other, the magnitude of the resultant vector is going to be the square root of F1 squared plus F2 squared plus F3 squared. And that's really all it is. But remember, you can only do this since they're perpendicular. Only since F1 is perpendicular to F2, which is perpendicular to F3. If they're not, you can't do that. Then you have to add vectors the way we were taught back in chapter 6. Okay, so this is going to be, well, F1 is 5,000, so that's going to be 5,000 squared plus 650 squared plus 6,000 squared. Oh, sorry, 600 squared, not 6,000. Okay, so grab your calculator. 5,000 squared plus 650 squared plus 600 squared square root. So that's about, what is that, 5,078 if I'm rounding to the nearest whole number. Now that's still a force, so the units for the force have to be in newtons. That is the magnitude of the force, so we're going to stop since that's what we needed to look for. My advice, after you're done this lesson, go to page 398 and review the summary concepts there. Well, this is a good practice to do every single time. There is a very long list of concepts this time, so I strongly encourage you to do that. I will also, like I said, put a link for the applet so you can play around with the 3-dimensional vectors and the octants to become familiar with them. So that is the end of lesson 7.4. So stay tuned next time for lesson 7.5.